So welcome again. In this class, we are going to discuss a current mirror. Basically, the current mirror is a way of practically realizing the current sources for our analog CMOS design. And so basically, what is a current mirror? Current mirrors, actually, mirrors are they produce the image of an object. So here you can see that. I think it is not coming. Yeah. Here you can see the mirror. There is the object. The image is there. But the current mirror produces the image of the current. I mean, it produces an image which is a current of a reference current, which is the object for that. So this will be a reference current, which is a highly stable current source, and it will produce an image that will fed to other circuits in our total design. And as you know that we can reduce the amplification, or the optical amplification of the image and object. So similarly, we can they are also scale up or scale down the current itself. Those image currents also there. So the scaling up and scaling down is also there. Actually, why do we need the current mirrors? Basically, if you are, do you have a course on DFAM? That I don't know. I mean, differential amplifiers. So the heart of the DFAM is a constant current source. The tail current source is the thing. And also, as we have seen in the earlier classes, that we can use the constant current source as a load to some topologies. It may be cascaded or simple, all these things. So the use of constant current source is there, and it is very important to learn about how they work or how we have to design these things. So the first is the simplest current mirrors. The simplest current mirror. Okay, I will draw it here first. Better. Actually, there is a as you may be aware of that we basically supply a single voltage to our whole chip. It may be 1.8 volt, 2.5, 3.3, whatever it may be. But but we need some intermediate voltages. This is the supply voltage feeding to our IC. But in the whole IC, we maybe need some intermediate voltage levels, 0.1 volt, 2 volt, 3, like that, 0.1, 0.2, 0.3, and also some currents. Okay. So there is a special circuit called bias BGR. There is a band gap reference, not bias, band gap reference circuit, BGR circuit, that will generate all these reference currents and voltages from a single supply. This is a very special type of circuit, and it is a very critical part of your IC design. And I think there is a class on how to design or how this BGR is working or all these things. So he will be taking that thing. So the BGR circuit is giving all these currents and voltages, intermediate voltages, and the only input to this is our VDD, this VDD. And also we can incorporate the temperature variation. I mean the insensitivity of these currents or voltages with respect to temperature. I mean, if you vary the operating temperature of the chip, the IC, this is the temperature. Suppose this is your designed current. You are plotting current here. This is the value of current for which you have designed your IC. I mean a particular subcircuit, call it SC subcircuit, designed for I0. But you will see that as the temperature changes, this I0, these won't remain constant. This will vary. Now, how it will vary? This is the question. It will vary like this, or that, or this one. This is the worst case. We don't want to have this or like this, but this is okay. Such a variation. So it won't vary much with temperature. So such kind of temperature insensitivity of these reference currents and voltages also can be made into the BGR. And also you may be aware of that there is a term called the process corner verification, variation, because suppose we have designed a W by L ratio of a transistor is 2.000 something, a perfect 2, but this is a mathematical singularity. No process can guarantee that your W by L will be 2. It may be 1.995, it may be 2.012 like this. So so there is a variation of your design parameters while fabricating the IC. So due to the variation also, this value of this reference currents and reference intermediate voltages will change. So that compensation also can be made into the BGR. So BGR is a views, it is a huge, it is a very important block that incorporates generating these voltages and currents, their temperature and process variation compensation also. So our reference current, so we will assume that BGR is generating a ideal reference current. In this class, we will be assuming that this IREF, this is a constant, temperature independent, process independent current, IREF. BGR is generating that, and we will using and we will be reflecting that particular current to all of our subcircuits, to many of us, whether we can use it scaled up version or in the scale down or the same current. So the basic topology will be like this. So this is our BGR, the current generating by the BGR, VDD. Suppose BGR is this one, so it is generating IREF, and this is our MOS. This is a diode connected MOS. And suppose here our diff amp is sitting here. The tail current source is this. This is M2, this is M1. This is called diff amp. Okay. So this IREF has to be reflected here. See, we can make it same. This call it I0. So we can make it I0 equal to IREF. We can make it greater than or less than. Okay. So how this will work is that we'll learn here. And we will replace, suppose for our understanding, we will replace we'll replace that diff amp with a simple load. So VDD, constant current source. I mean that this is the BGR, diode connected MOS. This is the load, RL. This is grounded. I0. Suppose we are interested only in producing I0 equal to IREF. So you have to prove that I0 is being really produced here. IREF is being really produced here. So this is, call it M2 and M1. You see that the VGS of VGS2 is equal to VGS1. These are shorted. The gate of this thing, these two transistors are shorted, and we have the equation of K by 2. K is some constant, that mu ox, mu C ox, all those things will be there. W by L of 2, VGS2, VTH2 multiplied by 1 plus lambda VDS2. And for I0 we have assuming both K for M1 and M2 are same, multiplied by 1 plus lambda VDS1. So this is the case, and we have this VGS2 equal to VGS1, and assume VTH also are same. These two, because this there won't be any body effect. Both of the body will be connected to the ground. So these VTHs are also same. And for the time being, assume that lambda is a very small. It is lambda tends to 0. So we can write it I0 by IREF all this will cancel. This K will go, W by L2, this one, VGS2 into VTH, VGS1 into VTH, assuming lambda is almost 0. So as our gate voltages are same, VGS2 equal to VGS1 and VTH are also same, so these two gets getting cancelled. So I0 will be ratio of their this W by L ratio, IREF. So if we have that, and normally that L, we can we normally do not change the L for our design. We will prefer to having the least possible L allowed by the transistor. So L of all this L of this transistor will be same. So we will change the W only. So L getting cancelled, W2 and W1 will be IREF. So if we have W2 equal to, I mean W2 greater than W1, we have I0 greater than IREF. Okay. If we have W2 equal to W1, I0 equal to, and we have, so this one. And in the while designing, what we do that, suppose W1 is some value, I mean say it is some integer multiple of some value n into W0. So and we will choose that W2 will be equal to m into W0. So this is going to be m by n IREF. So depending on the value of this ratio, we can generate a higher current here, we can generate the equal current, or we can generate a less current, I mean lesser current here, depending on this ratio. Okay. So this is the basic or the simplest current source we can have, but it has some problems. I mean here we have assumed that okay, the problems with the simplest current source are that due to the finite, here we have assumed that lambda is almost 0, but this is not the case, especially for our smaller device. I mean the short channel effect will be quite pronounced there, and due to the variation of lambda, due to having some finite lambda, those IREF, I mean IO by IREF will be equal to your W by L of 2 1 plus lambda VDS2 divided by 1 plus lambda VDS1. We have a circuit like this. This is M2, this is M1. This is our sum load, call it R. So VDS1, if VDS1 is not equal to VDS2, and also lambda is not 0, here lambda is not 0, then we cannot guarantee that just I mean just changing the W of M2 or M1 will guarantee the total or accurate replication of this IREF to I0. Okay. So this error term will be there. So for that we have to make either lambda 0 or VDS equal to I mean VDS2 equal to VDS1. This is 1, this is 2. This one. Okay. So this is one problem. Problem number and here in this graph in this plot, you can see that error factor, and as we have higher lambda is lower, it is higher than this, so this error increases. Okay, with the difference between them. This is the difference of VDS1 minus VDS2. As the difference increases, for a fixed lambda, error increases, and if the difference is fixed, so but as this lambda is increasing, the error increases. For a fixed difference, increasing lambda, error increases. For a fixed lambda, increasing error, increasing this difference, voltage difference, error increases. So this is the number one problem. This is the error due to the finite lambda. And also we have as I have told earlier, that no one guarantees you that you will get your exact design values in the IC. So though you have designed, you have assumed VTH1 equal to VTH2 for your design, but after fabrication, this won't be the case. There will be some mismatch between the VTHs. So this graph shows the error due to this mismatch of VTH. This is mismatch is increasing, I think the delta VTH error, and this is the reference current. Suppose we are producing a IREF is 1 microampere and VTH increases, so error increases. And for a fixed VTH, if our reference current increases, error also increases. It is due to the variation or mismatch between the two transistors. Mismatch, basically mismatch means mismatch of their VTHs. And this is the due to the layout mismatch. I mean, it is very difficult to have perfectly. Do you have any idea of how to make layout, analog layout of your circuits? Do you have any class on that? No, I think you will be having a class one more. Okay, leave it. Okay, just note the point that due to the layout mismatch also you will be having this, because your W by L, you have designed W by L2 and W by L1, suppose as a 2.00 that I was giving. So it is not, but after fabrication you may get this one 1200. So your WL will change, and that change in WL will also give a error in output resistance, also not output current also. So this is the third cause of that error in the simplest current source, simplest current mirror. So there are several ways to several ways to bypass these errors, these things. The most common they use is cascaded, I call it cascaded current source. This one is the cascaded. The circuit is actually this is the circuit, and there are actually this can be explained in two ways. One is this man, and the other is these two. And I will be giving you both the explanation and leave it to you to judge which is better. Okay. No. Suppose we are having so this is our cascaded current source, cascaded current mirror, this one. Resistance, this is I0, our output current, this is IREF. Okay. Now these two are our basic, this is our basics or simplest current mirror kind of thing, and this is the VDS1, this is VDS2, these two. We want to make this VDS1 equal to VDS2. This is our prime object. And to make this, we have to use two more transistor, M4 and M3. Okay. Suppose first that I0 is not equal to IREF. Assume. But whatever current is flowing through this transistor, it has to flow through this. Okay. So if we are assuming that lambda is not sufficient, it is very small. Lambda is almost 0. So same current is flowing through these two transistors, M1 as M2, means it demands that the VGS3 will have to be equal to VGS1. If we are assuming W by L and all BTH all are same for these two, so VGS3 will be equal to VGS1, and as it is shorted, so VGS1 will be equal to VGS2, and same current is flowing through this one. Same current is flowing through M4 and M2. So VGS2 should have to be equal to VGS4, and as this is shorted, these two have to be equal. So what we are getting here? Same voltage. This difference is also same. So we are getting VDS1 equal to VDS2. Now, if the circuit suffers from finite value of lambda, lambda is not equal to 0. But we have made this VDS1 and VDS2, so our I0 will be equal to IREF. Actually, there is a catch in this proof. It assumes that actually what does it assumes it lambda for M3 and M4 is 0, while lambda for M2 and M1 is not 0. But that should not be the case. When we are assuming that there is finite lambda, we have to assume that all 4 transistors having same or non-zero lambda. So this is the catch of this logic. This is due to Rajavi, and the second logic is more. I think it is better, and it is so. This Alan Holberg says that we are basically cascading M3 on M1. Okay, as I have said that cascading increases R out. I mean R out means the resistance looking between these two ports. It increases, and we know R out is some lambda effective I0. Here I am using lambda effective means basically because there are 2 transistors in series, so lambda effective means the effective lambda of both these transistors. So as R out increases, it increases means decreases. Okay. So though we have finite mismatch, suppose though we have finite mismatch between this VDS and that VDS. I mean here this hole and that, because of this lower or almost 0 lambda effective, we will be having I0 equal to IREF. Actually we can make this VDS, I mean VDS hole or VDS2 or VDS1, or the other way it is make the lambda to 0. So the second logic explains this circuit from this point of view. It makes the effective lambda between these two ports almost equal to 0. And so if though we have a finite mismatch between this VDS and that VDS, we are having I0 equal to IREF. Okay. So I think this explanation is better than this. Is that clear? Second expression means that okay, we are having this graph. If we can make this lambda very small, lambda is so we can reduce the error. Okay. Now this lambda is lambda for a particular transistor. So here what we are doing, we are cascading these 2 transistors, and we are measuring the effective lambda between these 2 ports. And as the cascading means higher output resistance, the output resistance will be much more higher than the single output resistance. And R out can be expressed in this fashion. So lambda will be R out. So effective lambda will be decreased. So though we have some mismatch between this VDS1 and this VDS and that VDS, not VDS1, this one, because of this small lambda, very small or almost 0 lambda, we will have this I0 equal to IREF. Because we will be having because say lambda is this much, if lambda still reduces, so we will get some curve like this. So this error ratio is almost equal to 0. Okay. So these are the 2 explanations of this. The operation of this cascaded current source, current mirror. And also one thing I would like to mention here, for the simplest current mirror, you just note that how the operating points move on their respective ID VDS plane. This is ID VDS2 means call it I0. This is I0. IREF VDS1. This is a drain to source connected, so it is this is our boundary. So it will be following this. Okay, sorry. So it will be following M1 will be following this path. If we here what we are changing, we are increasing the IREF from 0 to some value. So when IREF is 0, this path is open. So the voltage here also 0. So VDS 0, VGS is also 0. So it will start from here in this way and it will move along this line. Now see what happens for this thing, this M2. This is for M2. M2 means when I0 is when IREF is 0, I0 have to 0. So this is open. So here we get that VDD will come here. So here we will get VDD. So it will start from VDD and VGS 0. And if I0 as IREF is increases, I0 increases, so more and more voltage will be dropped across here. So less will be available for VDS2. It will be going like this, and up to and after some current, it will be hitting the triode zone here at point A. This one. So the transistor, so the but as I have explained that the current mirroring action is only will be taking place when this M2 and M1 will be in saturation. M1 is already guaranteed to be in saturation, M2, but M2 it starts from cutoff, goes through the saturation and enters in triode. So it will be valid. So the current mirror action will be valid for this zone only. So when it hits it, this point, and beyond that the current mirroring action won't be there. So so after this point I0 will not follow IREF. Okay. So this is our operation zone. I mean within this zone we can safely use the current mirrors, and we always try to have this voltage as minimum as possible, this one, because that will increase our operating range. If suppose if we having this this is the voltage of that lowest voltage, so we can use the current mirror from this one up to this range. So we will always try to reduce this voltage, I mean this heating point. Okay. So this is for the case for simplest current mirror. This is not okay. This is for simplest current mirror, M1 and M2. And well, for this one, for cascodate one, the things a little bit complicated in the sense there are so many things, because you see here I will draw all. Okay, I will draw in a phase space. M4. This will be for M2, M3 and M4. You see that M4 and M2 both are this diode connected, so they are guaranteed to operate in saturation zone. So they will follow this path. They start with VGS and VDS 0, and we are increasing the IREF from 0 to some value, some say infinity. So as IREF is 0, they will start from VDS and VGS both are 0. So they will start from this point, and they will remain in the saturation zone. But situation is different for M1 and M2. I mean I think I have made a mistake. M4 and M2 will be there. So this will be M2 and this is M3. But for M3 and M1 there the situation is different. Initially what happens when all of them are in saturation, this voltage and this voltage are same. So VDS1 and VDS2 will be same. So it will try to follow this one. M1 will the VDS, I mean this is the VDS1, this is the corresponding VDS also, VDS2, VDS4, VDS3. Okay, so initially this VDS1 will try to follow M2. So it will move along this as it is increases, it will also increase, and this will start from some VDD and move along this line M3. So the voltage across this one will increase, this one will decrease, and the total will be decreasing, because as we are increasing current, more voltage will be dropped here, so less will be available for this thing. So the total voltage has to decrease, but as we have virtually tied these 2 points, so it is increases, so it has to decrease. It is clear, the logic is clear. Total voltage is decreasing, this voltage increases because we have tied this point to this. So this point has to increase along with this point. So the voltage across this, the VDS3, it has to decrease. So it decreases. So after some time, it will hit the triode zone. Okay, and when it enters in the triode zone, this will no longer maintain these 2 voltages constant, because we have what logic we have used earlier. We have assumed that all these M4 and M3 will be operating in the saturation zone. Then only this VGS, these 2 VGS will be same. So if M3 comes out of saturation zone, it won't maintain, it cannot maintain this equality. So now this VDS1 cannot follow this VDS2. So it will go like this. This is the point A point, say up to A point, and ultimately it will enter in the triode zone also. Okay, this is a little bit involved thing. Is it clear? The movement of these points are clear. First it will follow with this up to this point. For this, beyond this point, it cannot maintain this equality. So VDS1 won't be equal to VDS2 further. So it will decrease, it has to decrease, because ultimately this voltage is decreasing, increasing the current. So as it is decreased, and you see that when it enters in the triode zone, the rate of decrement of VDS decreases. The rate at which it decreases, So as the total voltage decreases, so it has to decrease after some point. So this is the point after which it will decrease and it will hit the triode point. Okay. So the current mirror action will be valid from this zone, because it will remaining in the saturation. M1 remains in the saturation up to this point. We call this is B. But then what is the job of M3? But M3 actually what it does, M3 basically extends the using range, the usable range of this current mirror. Previously what was happening? Previously M3 also moving like this. So it will hit this point much earlier than this. Now here what is happening? It first moves along this plane, this line, and then goes this way. So that input range, that range will be increased with this point. So yeah, so this will be this will operate as a current mirror up to this point, and beyond this point it won't be act as a current mirror, and the I0 will not be equal to Iref there for this zone. Okay. Is that clear? This one. And also one thing I would like to mention here, that I should have mentioned earlier, because suppose this is the case of IV of a single, this is a separate case, ID versus VDS of a single NMOS. Yes, yeah, but if we are putting two NMOS in this way, the cascoding, then we have this kind of thing. This is a single cascode. you see that the effective resistance is much higher, and also this, okay, this will be like this. Also this minimum overdrive voltage is larger for cascoded structure. So if you do any simulation of the cascoded IV, you will get a more flatter curve here, and having a higher overdrive voltage. Which one?
In N2 and N4, in that case, does it start from VTH where the current is 0? The leftmost point.
This one?
That is VTH.
No, that is not VTH. That is actually VDS equal to VGS equal to 0. Because when there is no current, this is open, this path is open, so this point cannot be floated. I mean, it might have some voltage. So and this path is open, so this ground voltage will flow up to there. So this will be held at 0. As this is 0, so both of the voltages across this should be 0. And this is 0 means the gate of this strike to it 0. This is also 0. This is 0. So all are 0. So all of them, I mean, these also start with the same point, VDS equal to VGS equal to 0.
What is the path of the current when it's open?
When it open? When it opens, there is no path. Current is also 0. No, current. Okay, the current source means that if you have a current source there, and if you are not connecting that current source to anywhere, current will be 0. It cannot pass the current through anything. I mean, you need some resistance or some path or something to flow the current. So you are just keeping your current source open in open condition. Okay.
After that, sir, the transistor will become on only when VGS has crossed VTH.
Yeah.
So here the current is passing in and so.
No, that actually it will start from this. So up to some point, no current will be there. So and after it has crosses that VTH of the respective transistor, the current will start flow. Actually, you can verify all these things using simulations during your lab also. There is easy to verify all these things. Okay, this is clear. Okay, now the problem, it also has some problem, this cascaded, this kind of thing. As I have mentioned that the main problem of the cascade is the higher overdrive voltage. That means it reduces the output swing. As I have drawn in my earlier class, that if it is the case of one cascaded device, 2, 3 like this, so you will basically reduce the output swing. This is the point. This is suppose this is the allowed zone when all the transistors are in saturation. So basically you are reducing this thing, and this situation becomes more worse if it is more stringent if you are using, say, some low voltage of VDD, say 1 volt or 1.8 volt like that. So the same problem is here also, and to avoid this problem we have I think I should mention one thing here. The minimum voltage it can attain, see the minimum voltage across this V out, it can attain without going M3 and M1 simultaneously in saturation, is that 2 VOD plus VTH. Actually it should be in this one, I think. This is because that see this drain is virtually tied to this gate, because these two voltages are same, and these are connected. So this is basically virtually connected to this point. So it cannot basically go to the triode saturation boundary. So it can minimum it can attain is VOD plus VTH, but for this transistor, this point is not tied to this point, so this can independently move. So it can go, I think it will not be the case, yeah. So it can go up to VOD. So the total voltage, the minimum voltage you can get is this much, 2 VOD plus VTH. Okay. And to bypass this problem, we have some fancy circuits is here. So these are called high swing cascode or Wilson current mirror, Wilson CM. I mean, this is one topology, this is other. So first we'll discuss this one. The circuit for this here, what we do is that the gate of this M1 and M2 is connected to this point, and for M4 and M3 we are using a separate bias voltage VB. So what we gain here is that though these 2 points are tied together, I mean virtually tied together, this is not tied to the gate, because previously what was happening there, this voltage and this voltage are same, and this is connected to the shorted to the gate. So basically these two are shorted. So here, as this is not shorted, no path is there. So though we have these two voltages are same, the gate of this M1 and drain of this M1 is not connected. Okay, so it can attain the minimum voltage VOD across it, and the same thing also there. It also can attain the minimum voltage across it. So the total minimum voltage it can be attained is that 2 VOD, which is at least one threshold voltage less than the previous one. And threshold voltage is of the order of some 400 millivolt or like that, 400, 450 like that. And if you are using 1 volt supply, you are gaining 400 millivolt swing. So that's a use. So here actually here basically we decouple the gate to the drain of I mean for this M1. They are what, it's better if we can, yeah, this one. Here is M1, M1 is this. Here you see that here the M1 first moves along this path and then again follows this, but the I mean the course of the movement of this operating point of this M1 will be like that, directly like one. Previously it was moving some following this. Now M1 is moving along this path, so it can attain basically this VOD much earlier than this thing previous case. So it can so the minimum output voltage attainable is VOD across M1, and the same thing also for this thing. And also one more thing you can note that M2 is always in the triode region, because the VGS2 is addition, I mean is equal to VDS2 plus VDS4. Okay, so VGS2 is always higher than VDS2, so it will be operating always in triode region or in the triode saturation boundary, not in the deep triode region. Actually the path will be followed by this thing will be like this. It will start from here and go up to like this, and say this is your triode saturation boundary. So it will be within that zone. triode saturation zone, not in hard triode, not in hard saturation. So we can get high swing and also high output lambda effective due to the cascading effect using this high swing cascade transistor. And the second is the Wilson current mirror, is that that uses actually a circuit for this thing is like that. This is our VREF. It is the I0. Now first draw the M2 because it is the diode connected, so it will be always in. It will start with no, M2 start from here. It will go there. For M3 it will be like this, and for M1 also it will start from VDS 0 and move along this. This is for M1 because you see that M1 for M1 VGS 1 is equal to this VGS 1 equal to this thing. I mean that VGS plus, sorry, I should like this one. VDS 1 is equal to VGS 1 plus VGS 3. This is the VDS 1. This is equal to VGS 1 plus VGS 3. So you see that VDS is always greater than VGS 1. So it will be always in saturation zone. And M2 also. And for M3 this is the case. It will start from VDS 0. I mean when there is no current, it will start from 0. But for M2 it will start from cutoff, because when there is no current, this voltage will flow here, it will be VDD. So there is a finite voltage of across this and that also. So M3 and M2 it will start from some finite voltages, and if this voltage is finite, the gate voltage of this thing will also have to be finite one. So it will start VGS1 some positive value, some value will be there, some positive value. So you see that M1 is always ready to carry the current whenever even if there is no current is there. I mean at first the IREF is 0, so no current is flowing through this transistor, but it gets some VGS positive, and it can be shown that VGS1 is slightly greater than or equal to VTH of this transistor. So it is ready to get the current, carry the current. So as soon as you increase the current, it will the current flow through this transistor, and the same current will be copied here. Okay. And what happens for this thing? If it has some finite value here, it is 0. So M2 will start from some finite VGS and also some finite VDS. So this point will be some finite value of VGS and VDS also. And M3, it has some, because this is 0, this is 0. So this is 0. This has some finite value. So VGS is negative. So M3 starts from VGS negative value, and VDS3 some positive one. Okay, but the problem of this this Wilson CM is that it doesn't guarantee the VDS1 doesn't guarantee the equality of VDS1 and VDS2, because there is nothing, no transistor is there. So you can modify this circuit in this way. So now using the same principle or same logic we have used, these 2 points are tied to the same voltage, VDS of VDS1 and VDS2. So though we have finite lambda, we can have very good accuracy over using these circuits. So this is the Wilson current meter, or this you can say modified Wilson current. Okay. And one more thing I should say regarding this high swing cascade is that the generation of this voltage, this VV. Okay, because I told that the minimum attainable voltage is 2 VOD for this case, but that depends on whether the selection of this VV, bias voltage. You have to select a particular voltage to attain this thing. Otherwise, if you have select that VV greater than this particular VV0, call it VV0, this particular voltage, you will be having some higher. You will not be you will not be able to attain this 2 VOD. Because in that case, what will happen that M3 will move, M3 will enter the saturation before M1, or M1 will enter the saturation before M3. So both of them will not enter saturation simultaneously. So you have to choose this VV in such a way that M3 and M1 will enter the saturation. I mean, not saturation, triode. M3 and M1 will enter the triode in for the same current, same IRF. So for that particular current, you will be getting minimum output voltage 2 VOD here. So the generation of the this VV is also a point. Actually, this VV is generated in this way. They use and we'll be connecting this here. Okay. This is I0, IRF. So instead of connecting a separate voltage source there, we can use a R resistance and connect the gate of these two transistors here. Actually, the minimum VV we require is that 1 VOD plus, this is VGS3 plus VGS3. VV0 we require is that VOD plus VGS3, or we can write is VOD. This can be written as VOD plus VTH. I mean VTH of this thing of M3 and VOD of M3, and we are assuming that all the transistors having same sizes and all those things. So VOD of all the 4 transistors are same. So we are writing this thing. So we need 2 VOD plus VTH. Here what we are getting, 1 VOD we are getting here for this transistor, 1 VOD we are getting from this. So 2 VOD is there. So we need to choose this R in such a way that the voltage across this R, I mean IRF plus IRF into R will equal to VT, this VT. So we'll be getting this bias voltage from there. So we have 1 VOD, another VOD, VTH is there. So this is the minimum possible, I mean the VV or the gate voltage have to be used for these two transistors to attain the real minima, I mean real minimum output voltage here, that is the 2 VOD. Otherwise, if you choose VOD greater than VVO, you will get some higher voltage, higher minimum voltage across this point. Okay. So this is the case, and I think one last top. Yeah, this is the last topic we have. So these all till now what I have discussed is all this. Contd is there. Okay, you can see the results comparison between the this is the result for simplest current source, and this is the cascaded current source. You see that the minimum voltage is around 2 voltage, but for cascaded it is around 3. So the minimum output voltage required to maintain the constant current source or the I mean the current mirror action is higher for this topology, cascaded topology. These are all the reference currents. This is the output current. For 60 microampere, you will get this one. So beyond this point, I mean for this zone, you will getting the real current mirror action. This is the same case for here, and you see the accuracy is also, because it is not actually following. The current is somewhat increasing here, but here it is straight line, perfect straight line. So this inaccuracy is due to the mismatch of VDS and VDS1 and VDS2 there. As it is VDS1 equal to VDS2, the accuracy is much higher. This is the Wilson current meter. This was proposed by some G.R. Wilson 1968. Actually, he has proposed this thing for BJT, NPN BJT. So this is a version of, I mean, NMOS version of his NPN BJT, this thing. So we have Vmin I mean the Vmin for this and that are similar, but far less than the best, which is the 2 VOD. Is the best we can have. This is the improved or modified Wilson current meter. I have already drawn that. This is used to additional diode connected transistor that equalizes the VDS to, I mean these two VDSs. The terminology, this numbering of the transistor may be different, what we have used. And this is the comparison between the two Wilson sources. This is the first one, and this is the modified. You see that VDO, I mean that V min is much less than the cascaded one. It is around 2, but it was around 3. For cascaded, it was around 3. This mean. So it is around 2, but accuracy is not there. I mean, when it is 70 microamperes current, the reference current, it gives some 65.5 microampere there. This inaccuracy is due to the non-equality of VDS of those two transistors. This is the improved version. Actually, there is a mismatch. This should be this is a printing mistake in their book. This should be 6. I mean 67.5 microampere. This digit should be 6 instead of 7. You see that accuracy is much. This is 67. This line is 67. So 70 microampere current. It is almost 70. So we have much improved accuracy for this modified Wilson current sources. So there is a simple reason. I think I will discuss it in your lab session. You will be doing this design there. This is a high swing cascaded CM with following specs, and this is the active current mirror. Is the last topic. Till now, I have discussed about the passive current mirror. I mean, they are not amplifying the currents. So, but there is a type, or there is a special class of current mirrors that can that is known as active current mirrors, and I think that is used in the context of DFAMs. Okay, one more thing I should mention, that the NMOS current mirrors are known as the current sinks. PMOS current mirrors are known as the current sources. I mean this, like this. This is a PMOS IREF. So it sources the current to this load. So the current is entered into the circuit. So this is the source, current source. This is called the current source, and the NMOS one actually basically sinks the current. The current is going out of the circuit and going to the CM, I mean the current mirror. So it is the current sink. So for active current mirror, we use this current sourcing. These are two NMOS. This is our differential input, and this is the CM, current mirror, VDD. So this is known as the active current mirror. This is output. Actually, this circuit is more related to the differential amplifier class of sub-circuit. So I will discuss the detail in the next class, next DFAM class. Just check whether I am missing anything. Not much is there, and the explanation of this circuit is a little bit tricky because okay, let put a constant current source here. I mean that real source here, not an ideal one. So this is also a MOS, and so this current is being mirrored here, and these two are the input of the differential amplifier, and this is the load to this, and this is where the current mirror, the active current mirror, this pair, and what was the thing that I was mentioning is that actually if you analyze this circuit, it can be shown that, forget about this part, all five, I mean this, call this M1, M2, M3, M4 and M5, all these five transistors cannot be in saturation simultaneously. I mean the probability of staying in saturation of M1 and M4 are mutually exclusive. I mean if M1 is saturation, M4 cannot be in saturation, it should be having triode, and vice versa. I mean if M4 is in saturation, M1 have to be in triode. I think today is not much time is there, so I am leaving. I will explain this circuit in the next class, next DFAM class there. So anything is there? No, nothing. So that's the end.